Hello, everyone. I'm delighted to introduce today's guest, Michael Strevens, who is professor at New York University. He is specialized in the philosophy of science, and he has written amazing books on the topic. He has recently published a book entitled The Knowledge Machine. In this session, we talk about roots of modern science, the work of famous philosophers Karl Popper and Thomas Kuhn. Also, what is science, how science works, and what are the rules of science. So I hope you enjoy the conversation. Right. Hi, Michael. So let's start with the great thinkers of the world. So generally, either they join philosophy or they join science. You are a philosopher of science. So how did this happen?
Yeah, I wanted to have a little bit of both. So I started out more in the sciences, but discovered that I wasn't really cut out to be in the lab doing experiments. Anyway, got distracted by computers for a while. Took a philosophy class, discovered I liked thinking big thoughts, but I always wanted to be able to think big thoughts about science and in various ways, both about the content issues like that I work on, such as how to think about complex systems, and then thinking about science itself, which is the topic of my recent book. So that took me into philosophy, but in particular philosophy of science.
Yeah, right. I mean, of course, I think it has contributed a lot. Your latest book is amazing, for sure. And this is
Thanks.
so parts of it we'll discuss in today's session, and plus a little bit of other topics that we can include. So to start with, it seems like you were quite motivated with two great philosophers of science, Karl Popper and Thomas Kuhn. So what do you think? What were their contribution to philosophy of science? If you start with that.
Well, I think the way I see it, Popper's great contribution was to see that the key to scientific progress is to find small but decisively problematic difficulties in prevailing theories that end up overthrowing those theories. Popper thought that the way it was done was that individual scientists were all bent on refutation. I think it turns out psychologically to be a bit more complicated than that. Now, Kuhn had almost the opposite view of the mindset of your typical scientist. He thought that scientists were expected their prevailing methods to succeed, what he called the paradigm, which encompasses all sorts of things, prescriptions for what problems to solve, how to solve them, what kind of instruments to use, what kinds of theories or models to build. Anyway, Kuhn thought that scientists were totally wrapped up in these ideas and really couldn't imagine them being wrong. But that precisely because they were so confident, they would push the theories harder than a more skeptical person might have been inclined to do, and unwittingly discover the problems with the theories. So in a way, Popper and Kuhn agree on the overall contours of scientific progress. It happens by developing a theory, pushing it really hard, pushing it to breaking point, seeing that it fails, then coming up with some new idea that's better in certain ways, and repeating the whole process. So there's this pattern of constant destruction. They disagree completely about the mindset of scientists. Popper thinks that each individual scientist has, at least if they're any good, has internalized this destructive instinct, and they're all about attempting to falsify theories, as he put it. Whereas Kuhn thought almost the exact opposite, as I said, that the scientists were convinced their theories would succeed, and that's precisely because they applied them with such guileless confidence that they ended up destroying them.
Very interesting. Then what do you think? Where did they lack? What was the point that they missed, let's say, to define modern science?
Well, I think that they, and as I say, they both saw important things. Obviously, they can't both be right about scientists' attitudes. I think the truth about scientists' attitudes is somewhere in the middle. So scientists are not hopeless optimists about the theoretical framework, and sometimes they really are engaged, as Popper said, in attempts to refute theories. So a lot of in the news in the last decade or so, as bigger and bigger particle accelerators have been built, you'll find physicists saying, we want to destroy our current model. We want to find something wrong with it. Life is too boring with the standard model. It keeps getting things too right. We would love to find some anomalous phenomena, exactly the sort of thing that a Popperian scientist would be looking for and a Kuhnian scientist would never expect. So you have that critical attitude some of the time. Some of the time you have people simply going along with the way things are done because that's the way to make a career in science, and that looks a bit more Kuhnian. You also have a lot of well, I already alluded to it, a lot of careerism. So the way that science is set up is the rules that it's set up are often taken more like a kind of set of rules of a game that can be played better or worse, or for greater or lesser gain, but that where scientists sort of see themselves as playing the game as much to get ahead in their careers as to contribute to human knowledge. So so there's something in the middle there that has, I think, a lot of sociology of science and history of science has turned up in the last few decades, which is different from Popper or Kuhn. This sort of playing science for a game rather than having a purely, if you like, epistemic attitude towards it, just thinking of theories in terms of things that are surely wrong or surely right. And that's really important to my own conception of science. So what both Popper and Kuhn missed was the sociological dimension to science, I suppose you might say, where scientists are acting not like selfless seekers after knowledge, but like real human beings trying to make lives for themselves in the framework that's provided by what you might think of as the science game. Now, I don't want to say that they don't also take very seriously the contributions that science makes to the world, that they're not inspired by those contributions. But day to day, they're very much influenced by the rules that govern scientific publication, the rules that determine the distribution of credit among different scientists. And they play with an eye on the game that simply exists in a different dimension from these purely epistemic attitudes towards theories, whether they're likely to be wrong or right. And I see that as really important to the way science works. The ultimate point, of course, is not for science to be a game, or at least it's a very serious game. The point is to uncover the kind of knowledge that will contribute to human flourishing and insight into the way the world works. But science is so successful, I think, because the game is set up in such a way as to encourage players who are intent on making good moves to do the right kinds of things to advance that ultimate agenda.
Right. So there are already those key points that we'll be discussing today in the discussion, of course, about science game and how it's played and how science works, etc. But then before that, if we want to define what is science in general, like as a method, so what do you think? What is science?
Well, I think science, the right way to think about the nature of science is to look at these particular rules that have been laid down. Now, a lot of people have thought that we can think about science by looking at rules, but they've typically been looking for rules that I think are not the rules that really define science. So typically, they've looked for something called the scientific method, which is a kind of prescription for taking theories and evaluating them in the light of the evidence. There's no doubt that scientists, of course, do actually do that. I don't think many philosophers would agree that the general nature of the process is really any different from ordinary people's trying to find out about the world. So I want to know whether such and such a restaurant is a good place to eat out tonight. And I read the reviews, I ask my friends, maybe I have some knowledge of the chef's previous cooking and so on. And the way I think about answering that question is not really different in logical character from the way a scientist is trying to answer a question about, say, the true nature of gravity. So that's not what makes science special is not some particular way of answering questions in the light of facts. It's rather a very particular prescription for talking about this process. That is what makes science special. So the way I put it in my book is it's not so much a method or a logic, it's more like a speech code. Now that sounds like a strange claim to make, because how could a speech code be important enough to give science its special character? And in particular, I think, not just make it distinctive, but make it extraordinarily successful. Maybe would you like me to talk a little bit about that?
Yes, sure.
Okay. So I think the key here is that the speech code governs the what you might call the official channels of communication in science. So these are the science journals, some kinds of conference presentations and so on. The key is these are the places that a scientist has to present their work if they're going to make a name for themselves and influence other scientists. So everything they do has to flow through these channels. So the channels are critical to the whole enterprise of being a successful scientist, whatever your reason for wanting to be a successful scientist. And the most important rule governing what goes into these channels is a rule that says that only empirical evidence counts. Specifically, evidence that you can think of it as the kind of evidence that shows you whether a theory is making the right kinds of predictions or is able to explain the right sorts of things, where the right sorts of things are just the things we actually see. So we have to, the question of whether a theory is predictively or explanatorily successful is the only thing that matters in these official channels of communication. Now, that's going to sound maybe, again, like not that much of a big deal. Everyone already knows that science is all about empirical evidence. And so I think it takes a bit of imagination or a bit of historical perspective, maybe I should say, to see how something like science might be different without a rule like that. But I think we can have some sense of it simply by looking back to a time when this rule in particular, which I call the iron rule of explanation. You have to show that your theory is explanatorily successful or predictively successful. Look back to a time when that was not around, which doesn't necessarily take you very far back in time, just the beginning of the 17th century as the scientific revolution, the big one that sort of brought in modern science and the iron rule and the speech code I'm talking about. You go back to that period and look at what was going on, and what you see is in many ways a much more rich and holistic enterprise when it comes to trying to figure out how the world works. Rich and holistic because it brings in all sorts of information. So a thinker like Descartes is as René Descartes, the French philosopher, physicist, mathematician, is as interested, and biologist, psychologist, well, that says it all. He was interested in everything. He really wanted, there was no question about the universe that didn't intrigue him. And his way of answering those questions was to bring to bear all the methods he had at his fingertips. So on the one hand, there was at least a certain amount of thinking about the way that our conception of the world fits with revealed religion. But more important for him was philosophy and having a kind of philosophical system that treats, for example, the nature of causality in the right kind of way. He wanted all of this to work together to support his own particular views about why the planets orbit the sun and so on, why things fall to the earth, and what drives animals and humans to move around their environment doing the things they do. As I say, it's a very rich and holistic methodology that brings in philosophical considerations, considerations of overall harmony and elegance and explanation. What what the iron rule tells scientists to do several hundred years after Descartes is to do much less than that, to just focus on one particular kind of argument, namely this argument based on predictive power, something that Descartes cared about, but thought of as only one method among many methods for determining the correct, which theories ultimately was correct, which theory of gravity, for example, ultimately was correct. And so the iron rule, modern science, the most important thing about it, the key to the method, if you like, is to very much restrict, narrow down the kinds of arguments that can be made in official publications, thereby focusing scientists on just doing a single kind of thing. On the one hand, they're not supposed to, well, they can think what they like, but in their publications and the way that they present their ideas to other scientists and to the world, philosophy is forbidden. Any kind of philosophical considerations, any of these holistic questions about how it all fits together that was so important to Descartes, arguments based on the elegance or beauty of theories, not allowed. So scientists have to focus 100% in their public presentation on finding empirical evidence, and in the sense of sometimes what it consists in is very, very precise measurements that where one theory differs a little bit from the other theory, one of them is a little bit more successful than the other in getting the numbers exactly right. That turns out to be critical to progress in physics, or very precise descriptions of certain kinds of causal structures, like the genetic structures that are involved in biological development, and much else besides. It turns out, and Popper and Kuhn both knew this, and this is something they were really right about, that those kinds of facts, which are often extremely time-consuming to uncover, extremely expensive to uncover, and actually very tedious to uncover much of the time, are the facts that drive scientific progress, because they turn out to be the ultimate theoretical refuters. So someone like Descartes wasn't so much concerned with refuting, and that's why he wasn't making exact measurements of the speed with which things fell to the ground when dropped and so on. He was more interested in the kinds of arguments that support theories. But it turns out that really what we need for scientific progress is to, as Kuhn or Popper would put it, is to push our theories to breaking point and then to break them, and by breaking them to see that something else is needed.
Right. So for sure, if we really want to summarize or look at the scientific enterprise, which is basically working with empirical evidence. So a scientist would theorize, and according to Popper, the scientist will commit to the theory to falsify it, and then, or according to Kuhn, a scientist will commit to the theory to prove it, and if it won't be, or if he or she won't be able to do it, they'll end up just changing the theory itself, right? So here, of course, it seems like that both of them, they like, it makes sense, and of course the empirical evidence seems like the key to the scientific enterprise. But then where does knowledge machine, in terms of like your work, it fits in this picture?
Right. So what I do in my work is follows more or less the line of argument that we've been following in this conversation. I start out with Popper and Kuhn. I find this picture of refutation by incredibly concerted effort to uncover small details seems to me to be really at the heart of how science works. But the story about the psychology of scientists in both Popper and Kuhn seems wrong for different reasons for each thinker. And the work of the sociologists of science, for example, in the last few decades, that sort of brings out the extent to which scientists are game players, really inspired me to think of what I call the iron rule, this kind of the speech code, as being a critical part of the game, whose role is to get scientists to really focus on producing those little refuting facts. So it's it's like Popper and Kuhn in its emphasis on those facts, but there's a different psychological story about the motivation of science. And that psychological story zeroes in on what I take to be both the essence of science in the sense of the thing that sets it apart from what came before science, the sort of thing that Descartes was up to or Aristotle was up to. And that also is really what makes science so distinctively successful, is creation of a kind of institutional structure that channels scientists' psychology in such a way that they're directed towards frenetically finding these kinds of facts, whether they're personally interested in proving or refuting or whatever, it doesn't matter. They're digging up the right kinds of facts. So to me, the knowledge machine itself, which of course is science, operates by creating a social institution that motivates human beings, ordinary human beings, to focus their attention on a certain kind of fact that wasn't the kind of fact that seemed obvious, obviously seemed like the sort of fact that would lead to knowledge to thinkers like Descartes and Aristotle, who certainly are admirable minds. But that's the machine we've kind of almost stumbled across, if you like, this psychological machine for bending scientists' motivations by providing them with a certain very empirically centered game to play. And that's what's turned out to be so successful as a knowledge generating machine in the longer run.
Yes, right. So one interesting thing for me is that, so one way, of course, you named science as the knowledge machine, which is, of course, that makes sense. But then on the other hand, you also mentioned that the knowledge machine is irrational. So what do you think, why it is irrational?
Well, I think as I've said, it's the point of the iron rule is to narrow down the kinds of arguments that can be presented in official publications, so as to basically channel all of scientists' energy towards producing this one kind of fact. So insofar as that works really well, science as a whole makes a lot of sense. But there's something but it's interesting that narrowness, just considered in itself, not as part of this big machine that works so well, but just considered in itself, forces scientists to actually ignore kinds of arguments that they themselves think are not only valid, but even quite important to seeing the truth. So that might also almost sound like a contradiction in terms. I'm saying on the one hand, scientists are narrowed down in a way that means they avoid certain arguments. On the way, they themselves recognize the force of those arguments. It's important here to distinguish, on the one hand, the way a scientist can just think in the privacy of their own mind, any thoughts they like, unconstrained by the iron rule. And on the other hand, the fact that to play the science game, they have to then publish only some of those thoughts. So the narrowing is happening, as it were, as they consider what kinds of thoughts they can put on paper. So let me give a particular example I use, which I think has a lot of contemporary resonance, as the example of beauty in theories. So a lot of theoretical physicists convinced that the beauty or elegance or explanatory economy of a theory is an important sign of its truth, in the sense that by taking theories that have these aesthetic qualities or qualities of elegance and economy seriously, will be directed towards the true theory and away from false theories. The physicist Steven Weinberg, for example, the Nobel winner who died recently, said we wouldn't consider an ugly theory to be true. We would just know there was something, it couldn't possibly be right, and we would know that from its ugliness alone. A very strong statement. Whether he meant it literally or not, I'm not sure, but I think he meant it sincerely. So theoretical physicists will say they're guided by these considerations of beauty in their own thinking, and they consider them to be very important for distinguishing between promising theories and models and others. But then when it comes to publishing their theories and to discussing the plausibility of their theories, they're not allowed to talk about these very considerations that they think are valid and important. And that's the irrationality I'm talking about. It's an irrational narrowness that tells scientists this thing that you think is a very good, gives you really good reason to believe your theory is something you can't tell other scientists about, or at least you can't officially tell them about it. Of course, you can let on the side. And that's really weird, right? If all we were interested in doing was putting forward the best arguments we could for our theories, we should be able to do what Descartes and Aristotle did and give the aesthetic arguments as well as the empirical arguments, if we think they're good arguments, as many physicists do. But instead, we're not allowed to, which creates, first of all, on the one hand, a kind of this artificial game-like situation, which actually turns out to be so fruitful. And that's what I'm ultimately interested in, its fruitfulness. But also, I like to point out that there's something unreasonable about it, unreasonable in saying these good arguments cannot be advanced publicly. That's the irrationality I'm talking about. So science as a whole is great, but somewhere in that motivational engine, that institutional structure that influences the psychology of scientists in a way that makes science great, somewhere in there is a rule that actually demands of them to write in a way that is irrationally narrow.
Right. And that's why only the research or the science which is shown to the public, it's like less than 1% or something, which is generally communicated. Most of it is those theories or those experiments, concepts which were either they didn't work out or they were failed in general, and they are not even communicated to the public, at least.
Yeah, well, maybe it's worth saying that if a scientist is communicating directly to the public, writing a popular account of their work or of their field, it's fine for them to talk about beauty, and they often do. So they'll, in fact, spend quite a lot of time talking about the importance of beauty and finding and sort of giving clues to where the truth lies. That's one of the reasons we know, without having to go and interview them personally, although we can do that too. That's how we know that they really think it works. But then they're not going to get their promotions or their Nobel Prizes for writing these books for the public. They get them for what can be published in the journals. And the journals say empirical evidence only. This is one reason why, to take one recent example, Peter Higgs came up with his theory of the Higgs boson, which explains why particles get the mass that they have, back in the 1960s, when he was just a young theoretical physicist just starting out. And everyone immediately recognized that it was a really good idea. It pulled together in exactly these kinds of ways, gave a kind of compelling, economical, elegant explanation of where mass came from in particles, rather than physicists just having to say, well, we don't know, but here are the different masses of the different particles, and who knows where it comes from. So it was recognized immediately as a theoretical accomplishment. And yet at the same time, Higgs could not get a Nobel Prize until the experimental evidence for his theory had been uncovered, which is why he had to wait till I think he was 74 years old or something like that to actually get the prize. Now that's an example of the kind of tension that's at the heart of this scientific machine. On the one hand, a recognition that somebody there are really good reasons to take a theory seriously, and on the other hand, it's almost like a pretense that we can't treat the theory as a Nobel-worthy contribution until we're able to give the empirical argument for it.
Right, and that. I mean, of course, in this discussion, it already highlights the importance of empirical evidence. Then that also raises a question, then what is the importance of empirical evidence? In a sense, like what is the nature of it, and what counts as empirical evidence? So what do you think?
Well, I think in a way, the answer to that question is pretty straightforward. Think of a theory or a kind of an application of a theory to a particular situation, which scientists call a model, as laying out a kind of a typically causal story about how things work, a story that sometimes is able to make predictions about what will happen. Sometimes that's too hard, but it can make retrodictions, or at least it can provide explanations. But in each case, what you're doing is deriving some particular phenomenon from your model. And in particular, when I say phenomenon, I mean something that can be observed or at least measured, detected, whatever. So all of these models are making predictions or giving explanations, making retrodictions. And they will be to some extent specific about the thing that they're predicting or explaining. And empirical evidence is anything that tests those claims directly. And when I say directly, I mean that sort of when the theory says you'll see this happen, the particle will travel in this direction, or this gene will come to dominate the population, or inflation will rise for a while. When the theory says something like that, empirical evidence consists in going out and checking the prediction or the explanation and seeing whether this phenomenon actually does or did occur. And it's that simple. Right. In a way, the part of the development of modern science consists in simplifying this notion of evidence so that we're just looking at these consequences of theories and not worrying at all about the way that the theories do their predictions or explanations, but just sort of what phenomena they spit out at the other end.
Right. And basically you already mentioned about science game as well. But then when we are talking about experiments, empirical evidence, how the thing is that how it is selected at the end. Because there can be different scenarios, which of course you explain in your book as well, where two different people, if they are doing certain experiments, so how how far they can go in terms of explaining that empirical evidence, and at what point it is accepted in the scientific community that okay, one is right, the other is wrong.
Yeah, so the evidence comes in, and there's often quite a bit of disagreement about the significance of the evidence. There's so many. I said to characterize the nature of evidence is fairly simple, and part of what makes the game work the way it does is that the rules are clear and simple. But actually playing the game well is incredibly complicated. A big part of the complication is generating the evidence. Sometimes it takes billions of dollars and decades to generate the evidence, but typically, no matter, even with much less expensive science, a lot of effort and frustration and disappointment, and often, as you said earlier, things just don't work out. So there's that aspect of the difficulty of science, but also establishing the connection between the theory and the evidence can be quite complicated, just because a lot of assumptions have to go into your story to get from what may be some quite abstract theoretical posits to some prediction about what you'll see in a particular set of data on a particular photographic plate or whatever. And one of an example of this that's, again, simple but very important is that often scientists are using delicate, complicated measurement apparatus that frequently stops working or goes wrong or gets off kilter, gets miscalibrated. You need to produce the evidence, you have to get your apparatus to work correctly. But you're always susceptible when you publish results like this to have other scientists who favor other theories say, well, maybe these results look good for your theory, but maybe it was just the measurement apparatus going wrong. And maybe even you ran the experiment a few times and weren't getting the right results, and then finally you got the results you wanted and you published those. But in fact, your instrument was working fine and giving you the answers you didn't want. And then finally something went wrong with it, and that's why you got the answers you did want. Then you published them. So this is the kind of complication I'm talking about that has to do with the complications in the measuring apparatus, the complications in scientists' own motivational structures, if you like. The scientist I'm talking about is not deliberately misleading people, but just kind of happy finally to get the results they were looking for. And because of these kinds of complications, there can be a lot of disagreement early on in the scientific process about what the evidence actually shows. What for one person is a decisive demonstration of the correctness of one theory and the incorrectness of another. Another scientist will say, well, I don't know whether that gizmo was even working correctly when they got those numbers. So a kind of contention, or at least suspension of belief, is pretty typical of science in its early stages. Over time, as more and more experiments are done, you keep going back to the measuring instrument and making sure it's working properly. And this is assuming that scientists are sincere in their desire to get the stuff working, which I think is generally true. Over time, gradually, as the information comes in, maybe from many different labs and so on, the picture becomes a little bit more coherent. But it's difficult, tricky business getting these measurements, making these observations and so on. So often you get data that really clashes early on in the process, and it only in the longer term does a clearer picture emerge of even what these instruments are supposed to be showing us, let alone the ultimate truth about everything. This is the process I call Baconian convergence, naming it after Francis Bacon, who thought this kind of convergence was the way that scientists ultimately reached the truth. Bacon was pretty optimistic about the speed with which it would happen. In fact, sometimes it sounds like he thinks that once you get the facts, you can just do a bit of scientific research and figure stuff out in a few years' time. In fact, it often takes centuries.
Right.
But it does seem to happen in the end. And so in spite of the complications and confusion surrounding the evidence, we do at least often get convergence in the end.
Right. So of course, the Baconian convergence is like that it's a slow process that basically, again, in Kuhnian way, changes the paradigm from one paradigm to the other paradigm.
Yeah, I mean, I guess it can take, in Kuhn's classic picture, it's one great theoretical picture completely collapses into dust, and another completely different one is erected in its place. Now, even Kuhn had to admit, once people started looking at the history more closely, that it's often a bit more piecemeal than that. You know, one tower will be knocked down and another tower will be built. Sometimes the foundations are completely relaid, but often it's more like a lot of building a lot of extensions and doing a lot of renovation than like this wholesale redevelopment when theories change. But one way or another, you end up with something that looks pretty different typically from what you started with.
Right. I mean, that certainly sounds like Darwinian evolution, that slow change which accumulates, and then finally you get something new out of it. But then when this slow change is happening, at least the initial or before that change happens, there is this power struggles, which is, again, it's like human psychology part, but these power struggles which may also hold that change, right? One interesting example that you give between Charles Darwin and Lord Kelvin, where when Darwin proposed the theory of evolution, Kelvin said, no, it's not possible. So what do you think, that what are these power struggles, and is it still part of that irrationality of the knowledge machine?
Well, I think that's not so much a case of irrationality. I think it's just a case where the known facts are not enough to settle the question. So in the case you were talking about, Kelvin was using the thermodynamics to calculate how long the Earth had been cooling since its formation, and was able, by doing various calculations, to come up with an estimate for how old the Earth was, or at least how long it had been since the Earth had kind of settled down into a habitable planet. And it turned out Kelvin's estimates kept getting shorter and shorter. And it seemed like there just wasn't enough time for that kind of evolution, slow evolution by natural selection that Darwin was talking about, to have created this huge array of life that we find on the planet. So Kelvin thought that Darwin's explanation for the variety of life just couldn't be right because the Earth hadn't been around for long enough for evolution to have happened. Now, at the time he was making his calculations, he was doing it as best he could with the best information he had. He was aware of various weak points in the derivations and so on. He wasn't doing anything irrational. It did turn out that because he didn't know enough about the various aspects of the Earth's structure, that his estimate was far too short. In fact, it was off by a factor of about 100 or so, which meant that in fact there turned out to be plenty of time for evolution to have happened. But concerning his derivation, I think it would be wrong to say one side had better reasons than the other. That in particular, I don't think we should look back and say, well, just because Kelvin turned out to be wrong, he had less reason to believe his conclusions than Darwin and his allies had to disbelieve them. I think what really decided the question of belief was more social alliances. So the biologists tended to go along with Darwin because they wanted this great new theory to be correct, and the physicists tended to go along with Kelvin because he was doing something they recognized as good science, whereas what Darwin and the biologists were doing looked like some pretty far out speculation. They were both speculating to some extent. It turned out that it was Kelvin who had a key weakness in his speculations, but I would not say there was no doubt there was a certain amount of irrationality, as there always is in human affairs. But on the whole, both parties were simply doing their best to, if you like, win the game. No one was cheating. Everyone was following the rules. No one was being unreasonable. Both sides sincerely wanted to figure out the truth about the age of the Earth, but they ended up disagreeing vehemently. And in so doing, displaying a lot of the characteristics of human beings that we recognize so well. There was a lot of name calling and generally, I suppose, what they would have called in those days ungentlemanly behavior. But I would not say that there was irrationality, or at least no more than the usual portion that we find in human affairs.
Right. Which is basically a part of human psychology itself, and that will be also an interesting part of discussion, which we can do it afterwards. But before that, iron rule, which you postulate, it basically shows that, of course, you as a scientist, you follow an empirical evidence for your theories, but then there is also a bit of irrationality, but this mixture of irrationality and sort of rationality gives you at the end a final outcome of the scientific endeavor. So let's go through one more time from iron rule and how basically it molds the scientific studies.
Yes, sure. So the iron rule is this rule that says in official scientific publication, only empirical arguments count, only empirical evidence. And that actually a very narrow sense we were discussing earlier counts as a good argument. And that prescription, as I say, is itself irrationally narrow. It's telling scientists to ignore things that they believe are really important. However, scientists accept it as a rule of the game, and then they put all of their ingenuity and I would say rationality into following the rule, if that doesn't sound too crazy. So the rule itself is unreasonably narrow, but scientists say, okay, well, that's the rule. So what am I going to do? And then the vast combined mind power of all the world's scientists really goes to work trying to find ways that theories can be distinguished from one another empirically. Okay, I'm not allowed to argue that this theory is beautiful and this theory is ugly, therefore this one, the beautiful one, is the one we should believe. So I need to find some difference in the predictions they make, because that's the rules of the game. So they go to work trying to find some difference, and then they may go to work either personally or they'll recruit people to go out and actually test those predictions. One of the cases I discuss in my book is is Arthur Eddington's test of Einstein's theory of general relativity. Einstein's theory made predictions about the degree to which light would be bent by gravity. And the way to test those predictions, I'll just jump straight to the conclusion, is to observe the positions of stars very close to the sun. So where the starlight is traveling very close to this very large gravitational mass, the sun, and from the apparent positions of those stars to infer how much the light is being bent by gravity. You can then see whether Einstein's predictions come out right, or whether a theory like the old theory, Newton's theory, does a better job of predicting the bending angle. So they make different predictions about the amount of bending. Anyway, the only way to do this is to wait for a total solar eclipse. Otherwise, you can't see the stars that are right next to the sun. Now, Eddington was basically a theoretical physicist. He was one of the first people to really grasp the grandeur and brilliance of Einstein's theory, which involved very complicated mathematics. And he was convinced the theory was right, or certainly was on the right track, because of its mathematical beauty. So he was one of these theoretical physicists who thinks beauty is a really important guide to truth. But as I said, the iron rule says, sorry, that just doesn't count as an argument. If you're going to argue for this theory, you need to do some empirical measurements. So Eddington saw that an experiment like the eclipse experiment to measure the gravitational bending would be a test that would distinguish Einstein's theory from the prevailing theory, Newton's theory. The way to do it is to actually observe the stars during an eclipse. And then he went off and did it. So he actually spent the best part of a year sailing off to, it so happened a favorable eclipse was coming along a few years after Einstein came out with his theory, which actually was in the middle of the First World War. So not a very good time to go off sailing around the world anyway. But in 1919, once the war was over, and there was going to be a good eclipse, the zone of totality where the sun would be completely obscured, so where you would have to be to take the photos that would reveal the bending angle, was in the tropics. And Eddington himself led an expedition, actually a two-part expedition to one part with Eddington himself went to an island off the coast of Africa, Principe, and the other part went to a town in the middle, essentially, of the Amazon forest in the very north of Brazil, or nearby. Both very remote locations, especially in those days. And so Eddington spent almost a year of his life. He could have just sat down and explained the mathematics, and he was a great explainer. But because the iron rule said that didn't count, he spent the best part of a year of his life sailing off to the tropics to take this photograph. The whole thing hinged on it not being a cloudy day in Principe, where he was photographing the eclipse of the sun. So it was not just a arduous endeavor, but a very risky endeavor. And in fact, it was a cloudy day, and he didn't get very good data. Luckily, the Brazilian team got better data, although also some conflicting data, which is a different story, which I tell in the book. But never mind that for now. The key thing here is that the iron rule forced someone like Eddington to put aside what he regarded as certain kinds of good arguments for relativity and go off and get this at great personal cost, get this data that turned out to be ultimately a very important stepping stone on the road to coming to realize that Einstein's theory was decisively better than Newton's. So that's a good example of the iron rule at work, twisting a scientist's, not twisting in a bad sense, I should say redirecting a scientist's energy and attention to the kind of endeavor that ultimately turns out to be the more solid basis for scientific progress. But doing so in a way that asks them to actually ignore certain kinds of considerations that they think ought not to be ignored. Right. So Eddington, in short, was doing the right thing, the rational thing, to play the science game, and he was very successful. But it required him to do something that was, in a certain very important sense, unreasonable.
Yeah, I'll actually finish off that story so there were 3 telescopes, 2 were in Brazil, 1 in Africa, where Eddington was. And at the end, all 3 showed, like, one was in support of Einstein's, and the other 2, which were in Brazil, they were in support of of Newton, but then he still went ahead with the telescope that he had in Africa, and then they finally concluded that okay, Einstein's theory is correct. But let's say that maybe so that can be a luck, or can be that bias.
Yeah.
But
Well, certainly Eddington was strongly motivated to find reasons to hold up the data that pointed most directly to Einstein being right, and to sideline the other problematic data that made it look like maybe Einstein was wrong. And this is a good example. And again, I think he sincerely believed that Einstein was right, and that the pro-Einstein data was the best data. But there was a certain amount of political and social maneuvering to get other scientists to go along with this idea, and not all scientists did. So this is a good example of the sociological side of science. It's also a good example, ultimately, of the Baconian convergence I was talking about. So no one really knows what was up with those telescopes. Probably there was presumably something was going wrong with the telescope that made it look like Newton was right, although we'll never know exactly what. Eddington had a story he liked to tell, but he had no real evidence that his story was correct. But ultimately, many more measurements like this were made. So people continued to do these eclipse experiments, not as famously as Eddington, who did the very first one. But as the data came in from more and more experiments, it became clearer and clearer that Einstein was right. Sometimes the data, again, is problematic, but once you start to pile it up, and one pile just gets a lot higher than the others, and that's when most scientists start to come around and say, okay, well, I guess it's looking like Einstein, after all, is indeed correct.
Interesting. Yeah. Why I wanted to finish that story, because let's say that if Eddington would have been wrong, that later on, if they did the experiments and they found that no, Newton was right. So that itself shows me sort of a proofreading mechanism of science, that, okay, even if, let's say, you use your irrationality in the sense that you use your biases, which are, again, it's human biases, and you push one evidence over the other, but still science has that mechanism that they can sort of eliminate this thing later. Is it true? Does it make sense?
Yeah, no, absolutely. And you'll find a whole range of motivations, I think. So Eddington, Eddington presents this data as a clear success for Einstein. But not, as I say, some scientists who certainly knew what they were doing thought, well, the evidence is really not that clear. What happens next? Some scientists might have the kind of Popperian attitude, I want to destroy this theory. I'm going to take down Einstein by going back and doing more of these measurements and showing it's really Newton who's right. Other scientists might have more of a Kuhnian attitude. It's now relativity is here, and we've figured out one way to test it is to do these eclipse experiments. So I'm going to do lots more of them so as to prove Einstein right. And then still other scientists might say, well, I don't know whether Einstein is right or wrong, but obviously you can get a lot of attention and people will cite you a lot if you go and do these eclipse experiments, which Eddington has now shown me how to do. So I'll get some funding and go and do them, and hopefully I'll advance my career that way. So you have three motivations there: the Popperian desire to criticize and refute, the Kuhnian desire to bolster and advance the research program, and then just the purely sociological desire to advance your career by doing something that's recognized as producing important evidence. But in a way, it doesn't matter what the motivations are. The end result is going to be that people are going to continue making these measurements, and as those measurements pile up, then as long as we're at least sort of in the ballpark of being right about the feasibility of the experiments, we'll eventually get to see who's right and who's wrong. And it could have been Einstein who was wrong, could have been Newton who was right. But the way that the knowledge machine, the institutional structure of science just encourages scientists to keep on producing data, because that's what you need to do to play the game, whatever your reasons for playing it are. That's really what's most important of all, to to keep the data flowing in, to keep doing those experiments, not a single decisive experiment, the same experiment over and over again until you really get a clear picture of well, essentially how much light really is bent by gravity.
Right. So here, probably we can also think about human psychology itself, like for the science. I mean, it's clearly what it seems like that after billions of years of evolution, you get a species on the planet who is able to, reason and discuss and think about their own existence. And then it comes to a point where we have something like knowledge machine, a tool to really go ahead and ask those questions. But of course, when we look at the history of Earth and of course the history of humans, it's fairly recent. It's about 300-400, as you also mentioned. So what do you think, why it took so much time for the knowledge machine to arrive?
Oh, well, this is the other reason why I point to the irrationality of the iron rule. I think at least this really is speculation, but a really nice explanation for why people didn't start doing empirical inquiry in this way, that is by using the iron rule, by doing something like modern science, is that the iron rule looks dumb, crazy. It's saying you have all of these different styles of argument that can come together and help you to put together your picture of the world. Ignore most of them, just focus on this one. And that why would you do that? Why not use them all? If you think they're all good, use them all. So it seems like it doesn't look like a promising approach to take. If you were convinced that only empirical argument was any good and that none of these other forms of argument was any good, then it would make sense to do a kind of iron rule thing. But through history, including the contemporary theoretical physicists I was talking about who think beauty is important, we find people are not on the whole convinced that narrow empirical argument is the only valid form of argument. So the iron rule looks strange and unpromising, I think. What we really had to do was, for some reason, put it into practice and then see, wow, this is really working. Once it really starts to work, then you're, okay, it seems it's kind of narrow, but hey, look at what it's done for us. Finally, you have, well, a kind of empirical reason to follow the rule. But without already doing it, it's very hard to see that it's a good thing to do.
Yeah, actually, when I was reading about it, I was also thinking about apes. Once I started comparing, I was thinking that one thing is the way culture progresses in apes and of course in humans as well, which is from one generation to the other generation, and where, for example, in the wild, you can't argue again and again that this fruit whether I should eat or not, or to go to those places at certain time, etc. You can't take that risk, because if you take it, you are done. But in case of humans, once we reached at a point where there was already, that people were like, there were too many philosophers arguing, discussing, etc. So there was already a society where it was like more stable, and then that they could have conversations itself. It means they were not basically worried about the survival itself. So I mean, not taking the word in a literal sense of the ancestors, but exploring by themselves that what are these like different concepts in general, and then probably thinking about it, and I was like, oh, maybe this can be also a point where...
Oh yeah, no, that I think you're quite right that a kind of this sort of concerted empirical inquiry is a luxury. It's a luxury good, I mean, an important one, but so only in a society that is quite rich are you going to get this activity happening at least in a systematic way. But that kind of wealth has existed at times and places well before modern science came along. If you look at what Aristotle was up to, that kind of systematic philosophy is a luxury for very much the same reasons. And likewise, you see the same sort of level of systematic inquiry happening in the Arab world, in China for pretty much its entire history, and so on. So there have been many places and times where at least the material substrate that you would need to have a whole bunch of people just thinking thoughts about, say, how gravity works, that substrate has been in place, and people have in fact asked those questions. I'll just mention Aristotle again as a classic example. It's just that they haven't, even once the wealth of society reached that kind of level, they still didn't do it in this very remarkably particular and narrow way set out by the Iron Rule. So I guess what's coming out of this conversation is that there really is many things that are needed for science to emerge, and we can name some other things as well probably that are pretty important, like simply having the kind of material or technological culture to build scientific instruments like telescopes or air pumps and so on is also really important. You don't need them for every sort of science, but it's really hard to do a lot of science without simply having the glass blowing and the metallurgical techniques. So that's important too. There's much that's important, but I guess I have the Iron Rule on the brain, and so I'm focused on that as the single that I think maybe as the ingredient that came last.
Right. Exactly. Yeah. One or the other thing is that when we think of the knowledge machine, there were other products of the brain. I mean, religion, philosophy, but this seems like the only rational way of looking at things. If we, I mean, of course, deep down there can be irrationality, the way basically humans are making their these decisions to go for certain problems. But overall, when we look at it, I mean, for example, the questions like whether ghosts exist or not, right? I mean, before there could be, let's say, if there is wind and the door closes, and people would think, oh, no, maybe there was a ghost. But now we know that, okay, that there'll be, wind which may be pushing it, and somehow it was closed. And there we can see like how sort of this knowledge machine is working in a way to show that rationality to the people. So far it seems like this is the only rational method in that way for humanity, from humanity.
Well, I would make a case for philosophical thinking as being rational, sometimes at least. I think probably philosophers have done as much to dispel certain kinds of beliefs in the supernatural as scientists. So I don't know that science is the only rational way to do it. It's certainly by far the most successful way to do it. So at this stage, it can seem a little bit irrational to do it any way other than the scientific way. I'll certainly give you that. I think maybe, part of my story about why science took so long to arrive is that there are many rational modes of inquiry, and it was not at all obvious that this particular one, the one that science kind of, as it were, gambles everything on, would be so powerful, so much more successful than the others. Now we can look back and say, yeah, well, regardless of whether you're a religious believer or not, there's a real limit to the amount of useful information you can get about the material universe from revealed religion or from theological reasoning. Likewise, now we can look back and say, well, philosophizing turned out to be not so useful for constructing physics. Maybe it was important at certain critical junctures, but no one was just going to sit down and philosophize and come up with quantum mechanics, say. And so on. We can see those methods now were not as effective as we once took them to be, although I'm not going to say that they're completely useless. But that's only in hindsight, and it's not so much that we've figured out simply by thinking hard and clearly that science is the best way. It's more that we've discovered and kind of surprised ourselves empirically that some methods which look just as good as other methods have turned out to be much less effective, and the others more effective. So I would say we kind of stumbled into science and discovered its effectiveness more by accident almost than by figuring out in advance that this was the right way to get knowledge.
Yeah. So if we just continue in the same line, and we think about Popper's work, and he sort of also was, I don't know whether pissed off is a correct word for Freudian work, where he wanted to sort of, and that's also one of his motivation, was that he wanted to define science, what is science, but also define pseudoscience. So what do you think? What is pseudoscience, and how we can detect it?
That's a hard question for me. I know how I would define science, namely in terms of the iron rule. And I think something like the various schools of psychoanalysis, at least the way they developed after Freud, don't fit that definition of science because they don't attend 100% to empirical evidence in the narrow sense. To simply, it's not all about making predictions, for example, and testing those predictions, as Popper would have said. Now, so that means they're not science as such, although they are inquiry into the way the mind works, and so they have the same goals as science. Does that make them pseudo? I'm not sure I have any kind of characterization of the warrant for applying a kind of dismissive term like that to what's going on. It's certainly true that that there is such a thing as pseudoscience. There are certain kinds of ostensibly empirical inquiries which turn out to really have not a lot going for them and to be even intellectually bankrupt in some ways. Maybe it's better not to name anything in particular, but I think there are such things. But I suppose that I don't think of not following the iron rule as itself a vice, an intellectual vice, although it is turning away from something that's really productive. But it may be that not following the iron rule goes along with a lot of other things that are vices, like tendency to what they call motivated reasoning, confirmation bias, or for that matter, kind of the formation of cult-like social entities to promulgate ideas. I don't know. And so that whole collection of vices maybe is what characterizes some of the things people have called pseudosciences.
Yeah, right. So of course, when we are talking about pseudoscience, the other thing is, or basically it seems like it's the effect of human psychology in general. And when we are talking about human psychology, we can, and then, abiding with iron rule, the point there is that a lot of people, they don't understand science, or they don't really sort of discuss science in a way that, that what scientists are doing. And that's like majority of population when we are talking about in humans. So is it like probably they are incapable of understanding, or it's just the matter of education, that in one day, if we just educate like all the people, and they'll be able to understand it and discuss it? What do you think?
Well, I've written this book, which is an attempt to explain to regular people how science works. So I guess I'm pretty much committed to the proposition that people can, if they choose to put in a bit of work, understand what's going on. And, just the work that you need to read a 300-page book. So not hardly a lifetime of learning. So I think the basic ideas are simple enough to communicate to just about anyone. And recently I think people have had a bit of education to some extent in how science works from all of the toing and froing and confusion about the COVID pandemic. Questions like, is masking really effective? How is the virus transmitted anyway? Is it through contaminated surfaces? Is it through droplets? Is it through aerosols and so on? People got to see science in action in its very typical form, various scientists having very particular ideas and trying the best they could to argue for those ideas with different kinds of empirical evidence. But nevertheless, because the evidence was, at least at first, not nearly rich enough to settle the issue, and in fact, ending up with no really, science ended up with no clear overall picture in the early stages of the pandemic. And then later on, as knowledge accumulates, we can get more and more confident about some of these questions. Well, and we hope ultimately all of them. So there's a bit of an education in science going on there. Of course, doesn't include any of my more particular ideas about the iron rule. I think, though, it would be valuable to have as part of general education a story that familiarizes people with the degree. I think what may be most civically important, this is why I mentioned the COVID case, is to get people to see that just because when scientists are arguing with one another and disagreeing on how to interpret the evidence, that's not a sign that things have gone wrong. It's a sign that science is happening, that things are going right. Of course, it's incredibly frustrating when the lives of millions of people hang on it, that science can't give a clear answer. But that's the way it works. And it's important for people to see that it works that way so that they can recognize so that they know to be patient rather than just, going to the internet.
Right. So the other interesting thing here is that in general, how we look at things, right? Because when you say that, okay, scientists are arguing, because this generally happens. It also happened during the COVID times that there were different scientists having different observations, etc. But this is a way that the science works. But then I think it's also, when we are defining science, it's also important to define scientist as well. So who is a scientist? It's only the person who is going to the college, getting the degrees and stuff, like, or it's something more than that.
I think to be a scientist, you have to be part of the social institution of science, which means you have to be doing research and publishing that research or attempting to publish it in the scientific journals. And that's not to dismiss people who aren't doing that. In some ways, being a scientist is being this kind of person who subjects themselves to a weird and even irrational regime. So to not be a scientist, to be a more freewheeling thinker is hardly a terrible thing. But I will, as you might imagine, I will stick to my characterization of science using the iron rule and say a scientist is someone who's doing empirical research and publishing it in scientific journals, and therefore publishing it in accordance with the strictures of the iron rule.
Yes, because for me, in a way, it's also interesting. I was discussing with an ethologist a couple of weeks back, and so he mentioned that the science is basically like human play. Science, art, and music. It's like human play, and for sure, a person who may call himself or herself an artist, but just copying the art from someone or something like that they not doing something that innovative, that not doing something new as such. Would it be fair to call him or her artist, or it's just that a person hiding behind the degrees and the system?
I don't know the answer to that question about artists. I suppose, although if I were going to start giving an answer, I would be drawn to the kind of institutional theory that some philosophers have advanced, that to be an artist is to join into this social institution one way or another. And so in that sense, I would give an answer that's a little bit like the answer I give about scientists.
Right.
I don't know whether that's really right or wrong, but it seems like as good a place to start as any.
Yeah, no, I mean, as a philosopher of science, since you're trying to, be a policeman to define science, maybe to also go a bit further and, to define as who is a scientist as well in that methodology. That'll be
Well,
interesting.
maybe it would help to soften the police image if I said, I would regard myself as not being a scientist. I mean, I'm interested in figuring out how a certain thing works, namely science itself. But I'm not publishing my work in scientific journals, not this kind of work anyway, in scientific journals, and therefore I'm not publishing it under the aegis of the Iron Rule. And I'm kind of happy not to be doing that, because I like the more wide-ranging, free-thinking approach to these questions. So even as obviously, I recognize the power of the scientific way of doing things when it comes to almost any empirical question, I'm kind of happy also to hedge my bets a little bit, and in my own intellectual life, take advantage of the freedoms that come with not being a scientist.
Yes, exactly.
So I really, when I say it's okay not to be a scientist, I really mean that in a rather personal way.
Yeah, right. But also I mean, of course, we can give all the advantage and all the applause to the knowledge machine because of whatever we have today. But we can't sort of neglect the fact that most of these questions, they were asked already by the great thinkers, and and that this is what we need. We need, of course, we need science, but we need philosophy of science as well to sort of describe it, to keep it in a shaped way, to sort of that it just the knowledge machine works as it is supposed to work. So in that sense, for sure.
I will certainly agree with that.
Yeah. So yeah, we are, of course, almost at the end. Let's try to summarize the knowledge machine and the iron rule first. That the people, if they are looking forward to understand science, they should for sure read knowledge machine. But what are the things that they can expect? For me, it was thoroughly interesting. So many examples that you have included in the book. Uh, for sure, as there is a term called consciousness awareness, or consciousness raising, basically, that certainly happened with me once I read it. But what do you think? What else the general public can expect when they read this book?
Well, I suppose the things I wanted to get, the things that I thought it was most important to get across were, first of all, what we were just talking about, this picture of science as a often contentious activity with a lot of arguing back and forth, but that nevertheless makes sense in the long term. That picture is not an idea that's original to me in any way at all, but I think it's still it's important for any book about the nature of science to present that clearly to readers. And then there's my more particular idea about the Iron Rule, about what's special in science, consisting in this, as I put it, speech code, this rule about the kinds of arguments that can be published in scientific journals. I think that is my idea. And of course, I think it's an intriguing and interesting idea, and I would love people to bat it around and talk about it and bring it into their thinking about science. So I wrote the book mainly to lay out that idea in the way that, drawing as much as I could on historical examples, as you've said, on the kind of sociological work that sociologists of science have done. Of course, some philosophy too, but to make the best case for it that I possibly could. And so I suppose the reason to read the book is to, first of all, just get a more general idea about how science works, about what you should expect from science. And more specifically, if you're interested or intrigued by this idea, to see it laid out, explained, as you say, with the help of many examples, and just to kind of give it a little bit of a kick around and see if you like the sound of it.
Yes. So one thing that we can't neglect, which is the future of the knowledge machine, and when apart from humans, another intelligence which is emerging, it's artificial intelligence. So what do you think that if tomorrow we have robots doing the job? Can we get like more rational process, which will be more stringent, like in Popperian or in Kuhnian way, or still iron rule would rule the the game with robots?
Well, that's a very interesting question, since I've been, so much of what I've been spotlighting about the iron rule has to do with its power to motivate humans with their particular kind of psychology to do a certain thing, namely to focus, if not 100%, then 95% on the empirical evidence. So you might think, well, it's very indirect. Instead of just telling people to do this, we set up this whole game, and in such a way that if they want to play the game, they have to do this, whether they're thinking consciously about the fact they're doing it or not. If we could build artificial intelligence scientists, we wouldn't have to go through the circuitous route. We could just kind of program in an exclusive interest in empirical evidence. And maybe that's true. Then again, I suppose you might find that if you create an intelligence powerful enough to actually do that job in a really fruitful way, that intelligence will start kind of thinking philosophical thoughts, thinking about theoretical beauty. And so it will have to be reined back by the iron rule just as much as we flesh and blood humans have to be.
Right. That's certainly an interesting idea. So what do you think that if you want to correct something in the process of knowledge machine, if you want to like add something, chuck out something, I mean, for sure, there are these studies, right, that with every decade, we are increasing the IQ of people. Certainly, there is that more rational thinking coming into the system. So, do you think that already, we are going in that more organized way, or it can be like that sigmoidal way that uh, we are basically destroying the system? I don't know which one works better, or which one makes more sense.
Well, certainly from reading the news, I don't get the sense that more intelligence equals more rationality. I think we get a more concerted pursuit of whatever goals humans are determined to pursue. I don't know. I think science will need the iron rule for a long time to come.
Yeah, indeed. Right. So with that, if people want to read more about your work and want to, I don't know, contact you, what is the best way to find out more about your work?
Oh, well, yeah. So read my book. Sometimes I publish stuff online connected to science and so on. Take a look at that. You can always go to my webpage, which is just mylastname.org, to see what I've been up to recently. Or for that matter, send me an email and tell me what you're thinking.
Right. So
you'll find my email address on my webpage. So you just need to remember my last name, and that will lead you to all of these places.
Sure. And of course, I will put some details in the description as well. And with that, thank you so much for the great discussion and for your great contribution to the philosophy of science. After reading the book, I was for sure thinking that this should be included in the curriculum of the scientists, so that they should be able to read about it, think about it, and discuss about it, to, of course, make it more rigorous, the process, and make it much better. Thank you so much.
Well, thanks so much. This has been a great conversation.
Thank you.